Let's understand escape velocity. If VE is equal to escape velocity is minimum velocity with which body can escape Earth's gravitational field moving vertically upwards. So what is escape velocity? Escape velocity is minimum velocity that's required for a body to escape against Earth's gravitational field moving vertically upwards. So that's what is VE, that is escape velocity. Now, when we talk in terms of kinetic energy is half mv square. Now, since we are talking in terms of escape velocity, so it becomes half mve square. But at infinity, kinetic energy is 0. And at infinity, potential energy is also 0. Because your distance becomes infinity, so at infinity, potential energy is 0. So, what we can do is, we can sum both the energies, which would be equal to 0. Alright. So, obviously, we take this side and we take 2 there and we make root of it, square rooting both the sides. What we end up is with 2 gm upon r. This 2 has come from here and gm already is there. So, it is 2 gm upon r. Mind you, this gm can also be replaced by gr square, where g is acceleration due to gravity and r is obviously radius of Earth. Alright, if it is at the surface of the Earth then. So then the formula would change over to VE is equal to root 2gr, because we would have gr square over here, 1r would get cancelled, so escape velocity would be root 2gr. Mind you, this is on the surface of the Earth. Now if it is at a particular height, then this would be 2g small r. The small r is r capital R plus h, where capital R is radius of Earth. Alright, so that's the formula for escape velocity. Then when we come to critical velocity, in case of critical velocity is the gravitational force which is providing the centripetal force. So we can write it mvc square upon r, which is FCP, that is centripetal force, is equal to gravitational force gmm upon r square. Now on calculation, we get Vc is equal to gm upon r. Obviously, this r and 1r gets cancelled, this m and this m gets cancelled, and what we are left is gm upon r. And on rooting, square rooting on both the sides, what we end up is Vc is equal to, that is critical velocity is equal to gm upon r. Alright, where r is r plus h. Now again, as I explained above, gm is equal to gr square, so we can substitute that, and instead of that we can write gr square, and then the formula would be gr, root gr. So critical velocity closer to surface of the Earth, formula would be root gr, whereas we found escape velocity to be root 2 gr, and this can change with height. So instead of capital R, it would be small r. Here also instead of capital R, it would be small r. Alright, let's get into time period of satellite now. Now critical velocity that we found out earlier was root gm upon r, and critical velocity can also be written as 2 pi r upon t. Why? Because when we talk about critical velocity, it is this satellite which is moving in a circular orbit round the Earth. So circumference is 2 pi r and time period is capital T. Alright, so we can equilibrate both the formulae. Alright, where it is root gm upon r is equal to 2 pi r upon t. Obviously this m is mass of Earth. So first thing that we have got to do is squaring both the sides. On squaring both the sides, root disappears from here, and here it becomes 4 pi square r square upon t square. So if t square I take there and gm I bring it down. This one r which is there, I bring it here, so it becomes r cube. So 4 pi square r cube upon gm becomes our formula. So now we square root both the sides. So what we get is T is equal to 2 pi root of r cube upon gm. Mind you, again, this also we can replace it by gr square as we have done over here. When satellite revolving closer to Earth and applying gm is equal to gr square. Now this was when it's revolving at a distance from Earth. But when we intend to calculate time period very close to Earth, then we can replace gm by gr square, and on doing that the formula gets converted to 2 pi root of r over g. Alright, now let's get into kinetic energy of satellite. Kinetic energy of satellite is k is equal to half mvc square. Now since it's in a circular orbit, so we put in vc, not ve. Alright, so vc already we saw is root gm upon r when it is at a distance from Earth. So we just substituted there instead of vc. So what we end up is with half capital G m small g upon r, where g gravitation constant, mass of Earth, mass of satellite, and r is equal to r plus h, that is radius of Earth plus the height at which the satellite is encircling Earth. Now we come to binding energy of orbiting satellite. Now total energy is equal to Ke plus Pe. It's moving as well as it is at a height. So it has kinetic energy as well as potential energy. Kinetic energy half gmm upon r minus gmm upon r, the potential energy. So when we subtract, this is 1, this is half. So obviously this is greater. So it is minus half gmm upon r. So this is binding energy. So to unbind it, to strip satellite out of that binding energy, the unbinding energy would be positive of this value. Alright. So that's about binding energy. So what we did is binding energy of satellite, time period of satellite, we just saw critical velocity, then we saw escape velocity, we saw potential energy, we saw gravitational potential energy, then we also saw variation of g with depth, variation of g with altitude, and variation of g with latitude. Alright.